Hi all, I am going to explain our project idea as part of ICRA 2022 video submission. Reinforcement learning is a sequential decision making problem wherein an agent is trying to learn the optimal behavior through self-play in the environment. The feedback it tends to receive is this doses of positive rewards which it uses to reinforce optimal behavior. When it comes to robot learning, however, things get a bit complicated. Learning agent behavior on the robot might lead to cost and safety concerns. So what engineers tend to do is to learn an optimal agent behavior on the simulated model of the robot and then deploy it on the real world robot. However, it has been observed that a robot trained and deployed in this manner tends to perform suboptimally. The reason is often because the simulator and the real world environment differ considerably from each other. The difference might be because of a parametric misidentification or a failure to capture uncertainties entirely. This renders policy learning on the simulator to be suboptimal on the real world. For example, consider the following Cartpole environment with different gravitational parameters. We observe that for the same policy, the test environment tends to fail more often than the one in training. So, policy trained on the simulator will misidentify failure actions much more often and use it to deploy while testing, and this leads to suboptimal performance. In this project, we aim to reduce the sim to real gap by collecting data from the real robot and using it along with the simulator to learn an augmented reward RT prime that brings the performance calculated in the simulator much more closer to the real robot. It has been observed that the sim to real gap is directly proportional to the model of the real world robot to the model of the simulator. So in this project, we aim to calculate this ratio of transition probabilities of the robot versus the simulator and augment it in a certain manner to give us the performance of the real robot using just the simulator and this estimated ratio of transition probabilities. To calculate the ratio of transition probabilities, we use this existing result that helps us calculate the ratio of two distribution P and Q, which essentially rewrites the KL divergence as an optimization. An empirical form of this optimization is given in the slide. We calculate the ratio of transition probabilities by first calculating the ratio of state action state pair and then the state action pair and dividing them, which can be further used to give us the performance of a robot in the real world using the simulator.